Today we'll discuss some applications of exponential equations and specifically exponential growth and decay problems. General formula can be used for all these of y equals y sub o e to the kt power. Y is the final amount, y sub o is the initial, the growth and decay constant is k, and the time is t. And let's take a look at a couple of problems. So certain type of plutonium has a constant of decay of this value right here. How long is it going to take for 100 pounds to decompose to 5? So it looks like we've got quite a bit of information in this. We'll take the end amount, which is 5, beginning amount, which is 100. That's EK is negative 5.6 times 10 to the negative 5th power, and that's T. So we'll divide by 100 first, getting me 0.05. That's E to the negative 5.6 times 10 to the negative 5 power times T. Since this is a base of E, I'm going to use the natural log, so I take the natural log of 0.05 is equal to negative 5.6 times 10 to the negative 5th T, natural log of E, which we know this is equal to 1. So then all we have to do to get T by itself is divide, and I have the natural log of 0.05 over negative 5.6 times 10 to the negative 5th. And when we pop that into our calculator, and we get quite a big number of 53,495.22. That's going to be years. Next problem talks about carbon dating, and it says that you have initially 150 milligrams of carbon, and now you have 85. Half-life is going to be 5,570 years. Now, this is e to the kt power. It doesn't give us k, and it actually doesn't give us a t. That's what we're looking for. So we've got a problem here. We have two unknowns. But you'll notice in this problem, it does give us the number of years for a half-life. And the half-life is the number of years it takes for half of the matter to decay. So what I can do is I can say, all right, well, if I started out with 150 and went to 75, I would know that I still have an unknown K value, but my T time is 5,570 years. And after solving this problem, I could come back here and plug in K. So let's do that. This is 0.5 is equal to E to the 5570K, and then I'll take the natural log of both sides, and that's equal to 5570K ln E, which we know is 1. So natural log of 0.5 over 5570 is equal to K. And rather than take and find a decimal approximation for this, I'm going to keep it as is when I plug it in over here. It prevents some round off errors, which will be substantial if this gets really big or really small. So I have 85 equals 150 E raised to the ln 0.5 over 5570 T. And then here I'll take the natural log again. Whoops, this is multiplied. After I take and divide 85 by 150. And when I do that, I end up with a nasty decimal, so I'm not going to take and deal with that, but I'll reduce this to 17 over 30. E raised to the ln 0.5 over 5570. And now take the natural log of both sides. So this is the natural log of 17 over 35 is equal to the natural log 0.5 over 5570 times the natural log of e, which again I know is 1. And there's a t in there as well. So then multiply by the reciprocal to get my answer, and I get 5570 natural log 17 over 30 over the natural log of 0.5 is equal to t, which gets me to 4,564.21. That gets the problem done. All right, so in this problem, we have 500 bacteria initially present, and there's going to be 800 after an hour. Don't tell me my K, but I actually do have my time, and they want to know how many are present after 8 hours. Well, we need a K to be able to do that, so let's get that done first. It's 8/5 e to the K, natural log of both sides. It's K ln E, again, that's 1. So K is equal to the natural log of 8/5. And then over here, I want to know how many are left after a total of 8 hours. Well, if I start at 500, and I have E, K is now the natural log of 8/5, and the time is now 8 hours. This turns into a straight plug and chug problem in our calculator. And we end up with about 21,474.84 after 8 hours. And keep in mind, it's so big because it's growing exponentially. It goes up rather quickly. And it says now we've got this isotope and has a half-life, we've talked about that before, of about 28 minutes. And we want to know how long it would take for the given sample to decay to 37% of its original. All right, so this poses a couple problems. Number one, we don't know how much we're talking about. So what we could do is we could say y sub o, because that's what we start with, and we know some information about the half-life. So half of y sub o, e to the k, we don't know that, but we know it takes 28 minutes. So our time in this case is going to be in minutes when we get our answer. So when I solve this problem, take a look at what happens. The y sub o's drop immediately, and I've got 0.5 is equal to e to the 28k. I take the natural log of both sides, and I get 28k ln e. Again, this goes to 1. Divide by 28. And I get the k value. And then they want to know how long does it take to get to 37% of the original mass. So 0.37 y sub o is equal to y sub o e. Now I have the k value over 28. And we're looking for this time. So again, divide out the y sub o. 0.37 e to the ln 0.5 over 28 t, natural log both sides, equals the natural log of 0.5 over 28 t ln e. This again is 1. Multiply by the reciprocal, so I get 28 ln 0.37 over the natural log of 0.5 is equal to t, which gives us approximately 40.16 minutes. And that's all there is for today.